And let me just show you what I mean by that. I'm not fast enough with my iPad yet to switch screens really easily, so I'm just going to do it here. So if I say y equals sine of x, and we say y equals x, well, you'll notice when you zoom in really close that they're pretty close to the same line. We see them kind of diverge over there and over there, but right in the middle there, they're pretty close. And so what this means is, like, if I don't know the value of sine of 0.001 off the top of my head, I can actually guess that it is 0.001. It's going to be pretty close to that. Oop, I put a comma there. So, you know, it's 0.009999, but that's really close to 0.001. If I don't know off the top of my head 0.05, I could say it's probably close to 0.05. And it is. It's really close. It's 0.049. So the idea is basically sine of x is kind of a complicated function. We don't know. You guys, like, you know the unit circle, or you should. So we know a bunch of sine values. Like, I know sine of pi over 2 or pi over 4 or whatever. But, like, off the top of my head, do I know sine of 1, 2, 3, 4, 5? No, I don't. I would need a calculator for that or some sort of table. But for really teeny tiny values, again, think engineering. Think like you're writing some kind of program, or you're designing something with like really specific, very like tiny numbers with like a lot of precision. This is actually a good enough approximation, and if you're building something or designing something, and it's a way to do those calculations really quickly. So that's just like where it comes in handy. I don't know sine of 0.02, but it's about 0.02. So that's the idea. Let's see, how do I bring this back up here? So the idea here is using a tangent line and its y-coordinates to approximate the y-coordinates of a more complicated curve. And you can do yourself a little sketch of y equals x and y equals sine of x if you want on there. I forgot I can like draw an extra straight line. Oh yeah. Nice. Okay. So in order to do problems like this, we need to be able to write the equation of a tangent line. Do you guys feel like we've done problems like that before? We've written the equation of a tangent line. Yes, we've done those a whole bunch. Okay, so we're going to use that same, all those same things. So if I have some sort of curve here, y equals f of x, as we're writing the tangent line at x equals a, you know, we use point sub form, y minus f of a. This is going to be x minus a right there. And then how do we get the slope of the tangent line? F prime, yes, exactly. The derivative, f prime of a. And like I said, that's something crazy new or hyper advanced. Like, that's one of the first things that we learned how to do in calculus with derivatives, was write equations of tangent lines. Okay, and again, the idea is, you can kind of see it here on this curve, is that well, it's kind of weird looking on this curve, but basically this y coordinate here on the tangent line is approximating that y-coordinate right there. And like as long as they're close enough together, then that approximation is okay.
How do you determine if they're close enough together?
Basically, if the tangent line's at x equals 3, you could ask about 3.1, 3.2, 3.3. The further away you're going to get, the worse your approximation is going to be.
Okay.
In AB Calc, we're always going to be asking you very specifically, hey, approximate this value using this tangent line. So it's going to be pretty straightforward. But this is, again, kind of similar to what we were saying earlier. Like, this is something that you then build off of once you get to higher calculuses and higher engineerings and use it in different ways. So if you think like chemistry class, when you like calculate your percent error or whatever, this would be the kind of thing that you would bring that together in your engineering 101 as you're using this to approximate. Yeah.
How did you make that equation? Y equals.
So if I have a curve f of x, f of a is going to be the y coordinate at a. A is my x coordinate, and then f prime is the derivative, which gives me the slope of the tangent line.
Okay.
Yeah.
But then you move the f of a to the left side, and you made f prime equal to normal.
Let's do an example, and I think it'll be more clear. Yeah. Sometimes I think it gets, when we use too many letters, it gets a little bit in the weeds. Okay, so skip ahead 2 pages. What page is this? It's page 13. And we're going to look at number 2 right here. This is fun for me because this is from the 2008 AB exam. Anyone know why that's fun for me? Because I took it. Yes, that was my junior year, 2008, spring 2008. This is the one I took. That's fun. We'll see a couple other questions from that throughout this year. So here's the kind of question we're going to be asked. Again, it's very straightforward. It's saying we have a function f. We're told some information about f prime, f double prime. But notice we don't have a graph of f. We don't know the equation of f. We have very little information. We're trying to approximate f of 1.9 using the line tangent to the graph at x equals 2. So notice we can't actually find the value of 1.9 because we can't plug it in to the equation, right? We don't have the actual equation. We just have f of 2. We can imagine it's going to be pretty close to 1. All these answer choices are pretty close to 1. But we don't have actually any information about f. So we're going to use the tangent line to approximate it. So turn to your neighbor. What do you think your steps are going to be in order to do this? Talk about it.
Okay, tell me what the answer is. No, do we even have to do any work?
So we could probably write like.
Plug it into the thing, so it's like the slope.
If it's 1.9, it's going to be negative 0.1 times 4 is negative 0.4, and add 1 to that.
So the tangent line that
Right? This is our equation.
Yeah, you're right.
Okay, so your first step here is make sure you write the equation of the tangent line at x equals 2. So what is that tangent line equation going to look like? It's going to be y minus 1 equals 4 x minus 2. Okay, so there's the tangent line to the graph. We have the y coordinate. We have the slope. Great. Now, to approximate f of 1.9, we're going to find the value of 1.9 on the tangent line instead of on the actual curve, which means do what with 1.9? Yes. Yeah, we're just going to plug 1.9 in for x here. So this would be y equals, I'm just going to add 1 to both sides as well.
It's negative 1.1.
And then we just solve. So you are going to have to do some math with decimals here, and that's okay. So we get 0.6, and that's answer choice B. Now what 0.6 actually is the y-coordinate on the tangent line. But it's approximating what the y-coordinate on the curve is. Like we said, it's close to 1. It's got a pretty steep slope there of 4. But that's the idea. Okay, so great question. In this question right now, no, f double prime is not relevant. Sometimes you'll be asked, is this an overestimate or an underestimate? So talk about that with your neighbor.
It would be an underestimate because it's under the
It's concave up in the tangent, or be below the curve.
Yeah.
I think I get it now. It's just really close to those lines, getting like okay, close to the
I get it.
I know. I don't get the. I
Me too.
I still don't get linearization in physics.
It's concave on
Yeah, I don't know what it is in physics.
Yeah, like,
then if you have a
like,
tangent line, it would be like
it's really weird. You have to find like the actual.
Are we doing? Oh wait, yeah, you're right.
Like linearized, where I get to make the actual linearized graph.
Okay, so is this overestimate or underestimate? Under 4K. Why?
Because it's concave up and the tangent line's below the curve.
Yes. So f double prime is 2 of 2 is greater than 0. So f of x is concave up, which means the tangent line is below the curve. That's actually the definition of concave up. So anything that's concave up, the tangent line will always be underneath the curve. So if we're taking values from the tangent line, they're always going to be lower than the value of the curve at that point. So yeah, in this question they didn't ask that, but they did include the second derivative just for fun. But I have seen a lot of FRQs where you have to find the second derivative and decide if it's an overestimate or underestimate. Okay. Any other questions? Okay. Do number 3. All right, guys, let's check here. So our first step here is we need to make the tangent line at x equals what? 0. Okay. So everything that we're doing is about x equals 0. So sometimes a common mistake that's made is using 0.012 or using the value that we're trying to approximate, using that too early on. Everything we're doing is about x equals 0. So we make the tangent line at x equals 0, we find the y-coordinate at x equals 0, and then we approximate. So first we need to know what is the y-coordinate at x equals 0? 2. All right. We need to know y prime to find the slope of the tangent line. What does y prime equal?
Wait, what?
Yeah, there's gonna be a 1/4 in there. Okay, so it's 1/2 4 plus sine x to the negative 1/2, or 1/2 root 4 plus sine
Times.
times cosine of x. Yeah. Okay, again, this little shortcut here for remembering that the derivative of root x is 1 over 2 root x. It works in these more complicated ones as well, and it helps you do it kind of quickly. So then when we do y prime of 0, what does that equal? 1/4. So that's our slope of the tangent line. So our tangent line equation then is y minus 2 equals 1/4 x minus 0, because it's all at 0. And then so we can just add 2 to the other side. So here's our tangent line. Once we have the tangent line, what do we do? Yeah. Yep. So we just say 1/4 times 0.12 plus 2. So it's just 0.03 plus 2, 2.03. Which is B. Questions on that process? Okay. Again, this is like usually what you're going to be asked to do. You're just going to say approximate this value using this tangent line. So you just have to make the tangent line and then plug in that number. We rarely see questions like number 4 anymore. So we won't do that one today. But it's much more like this. Just make a specific tangent line and plug in a point to approximate it. Okay, questions? All right, we're also going to look at average value today, which is in a few pages here. On page 15. I don't know. I haven't done it yet. I forget how to do it.
It says using small values, so I just use 0.
Yeah. I haven't looked at it since last year, so I don't remember how to do it right now. All right, so we have a formula here for the average value of a function. Here's the formula. It's written in a couple different places. You could also write it this way. Delta Math likes to write it this way. I mean, it's, they're the same thing, right? But just be on the lookout for seeing it written both ways. Whatever way is easier for you, you can write it that way. Average value, another way to think of what average value tells us, is it tells us the average y coordinate that a function has. So a great example that's easy to think about here is if I think of the graph y equals sine of x, it goes on forever in both directions like that. What's the average y coordinate of sine of x? 0, right? It goes up, it goes down, but on average, it's 0. That's what average value tells us. So this is going to fit in with a lot of our word problems and a lot of our rate in, rate out, or particle motion, things like that. And it's something that's going to be useful for us to find. But it's very easily confused with average rate of change because they both use the word average. They both involve dividing by something. And so it's just really important that you read the question, you know what you're trying to find, you know what you're given, and that helps you decide which formula to use. You do have to memorize that formula, so just go ahead and memorize it. But let me just illustrate this using a particle motion example here. So let's say we have velocity. Let's say this is measured in meters per second. And I'm going to integrate velocity from 0 to 10, let's say. Turn to your neighbor. If we do that, what will that tell us? Let's just make up a number here. Let's say that equals 15. What does that number mean in the context of the problem?
It's gone 15 meters. And if you divide by the starting and ending points, you get your average.
Okay. There's the context. Particles moving on the x-axis, that's the velocity.
It's moved 15 meters to the right.
Okay. So, being as specific as possible, what does that 15 represent? Can you be more specific?
Displacement from 0 to 10 seconds.
Okay. Explain it like I'm in 5th grade. What does that 15 mean?
How much is the particle? How distance the particle has moved in 10 seconds?
After 10 seconds, it has moved 15 meters to the right.
Okay, after 10 seconds, it's moved 15 meters to the right. Distance that the particle has moved. Let's be careful because if this particle, had its Apple Watch on, did it take 15 steps? Not necessarily. It could have. Could have taken exactly 15 steps.
Well, 15 meters, right?
Yeah. So, did the particle travel 15 meters, or is the particle 15 meters away from where it started? 15 meters away from where it started. Okay, so that's what displacement means, right? So it could have gone back and forth a bunch of times. My displacement between 8:10 and 2:55 is just about 0 because the day starts, I'm here, and the day ends, I'm usually around here somewhere. Distance travel is way higher because I'm walking around like a maniac. So yeah, this is just, it's 15 meters away from where it started. Okay. To the right specifically, yes. Okay, so let's say I take that and divide it by 10 seconds. Turn to your neighbor. What does that tell us? What do we learn from that?
Your average is y per second.
Displacement per second.
What is the y displaced per?
Is
Wait, displacement per second.
Average displacement per
Okay, this top part is 15. 15 what? Meters. 15 meters over 10 seconds. So this is 3/2 meters per second. What am I measuring here? Average displacement in meters per second? Average velocity. This is the average velocity that the particle traveled. Because it's meters per second, right? That's a speed measurement. That's a velocity measurement. This is the average velocity. Because basically it took the particle 10 seconds to go 15 meters. Now, is it possible that the particle was actually traveling way faster than that during this? Yeah, it could have been going back and forth like a crazy person or a crazy particle. But it took 10 seconds to travel 15 meters. That's the average velocity. What this is the average value formula applied to velocity. And so what we're noticing is the units will be whatever the function f is measured in. So what we were integrating was velocity. And so our answer is velocity. Our original function velocity is in meters per second. Our average value is in meters per second. Now, first we did integrate to get to displacement, but then we divided that again by time. So it's not telling us average displacement or average acceleration. It's telling us the average value of whatever function it is that we're talking about. So if we do this to velocity, it tells us the average velocity. If we do this to temperature, a temperature function, it tells us the average temperature. If we do this to a rate function, it tells us the average rates. It tells us the average y-coordinate of whatever it is that we're looking at there. Okay. This is how I was actually thinking about this on the way to work today. So I was driving my wife's car, and it tells you like the average speed on your trip or whatever. And the way that it does that is not just by averaging together all of the speeds that you're going at all the time. It's just dividing the total distance you drive by the amount of time that you've been driving for. Right? That's just how our car works. It's just distance over time. So anyways, I thought of that today. Okay, so speaking of temperature, look at question 113. I want you guys to set up the equation to solve this. Okay, so for this question right here, should we use the average value formula?
Yes.
Yes, we should. We are told a function that tells us the temperature, and we are looking for the average temperature. So that's what we want average value for. So this would be, what would be our bounds for integrating here? Yes, 13.5 to 18.5. That has to do with our time since midnight is t equals 0. So this would be hours after midnight. 18, yep, sorry. Look at that, fancy. Okay, and then divided by? Yep. It's d? I don't know. Okay, but that's the setup. Okay, now here's what you want to be on the lookout for. Questions that would give you all this information here, but instead of saying what's the average temperature, maybe it says what's the average change in temperature between those two times. Like every day from 1:30 to 6 p.m., how much does the temperature usually change? What would be different about how we would solve this? Talk to your neighbor about it.
Averaging change. Where you take the derivative and then you just plug in your whatever. Yeah.
The derivative of the
like if it was 136, but like oh wait, it's supposed to be 13.5 instead of 4.5.
Yeah, 13.5. That's 13. Oh, that's not 13. Yeah, you're right. You're right.
B.5.
B.5.
18 minus 30. It's like after B minus 100. I think.
Because isn't that just the one? Yeah. So
same thing, but just t is
Oh. Hello?
Yeah, because this isn't like a real debate.
That makes sense to me.
Okay. Why? Why is it doing it like this? I don't understand. You know, having new technology never makes things simpler. It just means that you can do more. But it's always more complicated and always takes more effort. It's true. Anyone that says technology is going to make your life easier, it's a lie. It's always a lie. Anyways. So if we're doing average change in temperature, now maybe I should have said average rate of change of temperature, because average change in temperature would just be T of 18 minus T of 13.5. Because that's the daily temperature, so the normal change in temperature would be that many degrees. Average rate of change of temperature would be that over 18 minus 13.5.
So it's just average rate of change.
Yeah, it's just average rate of change. Yeah. So you just got to be on the lookout. What does the question give us? What are we asking for? We're actually going to look at a couple examples of that right now on Delta Math. See, like, why doesn't it go the full window right there? I don't know. Why do I have to press this again? No one knows. Okay, so here's some questions that you're going to see on your homework tonight. We don't need to solve these or set anything up because you're going to get to do that for homework. But would you use average value or average rate of change to talk about with your neighbor? And so does that mean slope or integral? So which one is this? Yeah, this is integral. It says average value, right? So we're going to need to do, there's the average value formula. Okay. See, that's the fancy thing that I can do from mine on Delta Math. Oh, this is still the old Delta Math format. Yours doesn't look like this anymore, right? You got the new stuff. Okay. Let's see, new problem. Okay, read this one. Which formula would you use and what does that involve doing? Okay. Now I know we can see the keywords in there, average rate of change, right? It's written right there. So we know we're supposed to be doing slope. But notice, if we're trying to find the average rate of change of G, G is an integral of F. So when we're finding our slope, G of 1 minus G of negative 3 over 1 minus negative 3, we're going to have to be plugging those numbers into an integral to get those values. So just because it says average rate of change doesn't mean we're not using integrals at all. We have to base it on the problem. But this is our goal here, to use that formula with whatever G happens to be. G happens to be a special type of function called an accumulation function. So we are going to need to use the integral, but we have a calculator to do all that. So notice we're calculating G of 1, G of negative 3, and dividing it, etc. Okay, let's see. I want to find, what do I want to find? And, how easy is this going to be for me on my iPad here? We'll find out. Yes. Oh, don't look at the grades. Okay. Okay. Read this. Let's call these choices A, B, C, D in order there. Turn to your neighbor. Which one is it going to be and why?
then yes.
So yeah, you want to use
Yeah, wait, maybe you're
We're doing the average temperature and then the function is for temperature.
yeah. The second one you can use
So you thought it was easy, huh?
I think.
Okay, raise your hand if you think it's A. B? C? D? Okay. The answer is A. The answer is A. So when we see this 1/10 in the integral from 0 to 10, that's telling us average value. And it's average value of whatever is in the thingy. So this is going to tell us, the first one is going to tell us average value of velocity, which means average velocity. It's going to give us the average y-coordinate of the velocity graph, which is our average velocity. C is going to give us average what? Acceleration. What is B going to tell us? Average rate of change of velocity, also known as average acceleration. So B and C are actually telling us the same thing. Two different ways of calculating it. One is using velocity, basically estimating the derivative. One is using average value of acceleration. D is average rate of change of acceleration, which would be average jerk. Yes, the average jerk. Yes. Okay. Okay. I'm so glad these two came up one right after another. It was random, so I couldn't control it, but talk about this one. B is correct. Okay, so notice what we're missing now, we don't have the formula for average value of velocity. That would tell us the right answer. Instead, what we have as the right answer is B, which is the average rate of change of position. But those are the same thing. Rate of change of position is velocity. So it's two different ways of calculating it. Let's see. What? Yeah, we already talked about all this. So that's average acceleration, average velocity, displacement, how far the particle moves, or distance from the starting point. Is that way to say it? Average acceleration. So, like I said, I wish I could have planned that those two were going to come up, but I'm glad it worked out. When we talk about average velocity, let me just write this in here on our notes. This is the one that comes up the most. You can either do the average value formula for the velocity function, or you can do average rate of change on position. Somebody tell me something about these two things right here. They're the same. When we integrate v, what function do we get? We integrate v. We get x, we get position. Right? So if we're doing a definite integral of velocity from a to b, that's going to be x of b minus x of a. Divided by b minus a, oh, there it is. They're actually just mathematically the same thing as well. Now, what determines which one you use? It's what function you have to start with. If you have the position function and I want average velocity, you do slope. If you have the velocity function and I want average velocity, you do average value. It just depends on what you're given. So make sure you read. Make sure you read, make sure you see what you have, what you're looking for. That'll determine what formula you need to use. The more we learn in calculus, the more abilities you guys are going to have to calculate all different kinds of stuff with all different kinds of information. So the key is really just remember what each formula does, and that'll tell you when you need to use it. Well, that's perfect timing.